Hello and welcome to Class Time Mathematics. All right, so today we'll be looking at graphical solution of simultaneous linear equations. So the objectives for today are write linear equations in slope-intercept form
and solve a pair of simultaneous linear equations in two unknown graphically.
Okay, so let us look at the situation here.
So Nikisha, let's take a little trip together.
Yes.
Right? We're going on vacation. Imagine that we are going to be taking a taxi while we're on vacation.
All right.
And you know that the taxi service charges $200 to pick up our family. And from the hotel, another $15 per kilometer for the trip. So
you're saying $200 for the taxi to come and pick us up?
Yes.
And then when it start moving, we start paying $15 per kilometer.
Exactly.
So what are we getting at? We want to know how much money to spend because we have to be on budget. So we can't go over budget. So we need to know how much it would cost for maybe a short trip, maybe 8 kilometers.
Yes, and these are some of the real-time applications, real-world applications of math.
Yes, specifically linear equation. Now, how could we represent this? How could we find out? What mathematical method could we use?
I'm thinking this would look awesome on a graph.
On a graph?
Yes.
Oh, interesting. But what do we need? What are some of the things that we'll need to create that graph?
I'm seeing some of the information there, and I'm seeing $200
yes.
as the fixed cost, because it doesn't really matter whether or not how far the journey is. That
yes.
taxi driver is going to charge us $200 at least. And he's going to charge us an additional $15 per kilometer. So we need to take that into consideration as well.
So maybe we could set up an equation.
Yes.
An equation to represent this. So an equation, I'm thinking, would look, so the Y here would represent what?
The total cost that the taxi driver would, the total charge for the taxi service.
For the service, yes. And this $15, I'm thinking, would represent the cost per kilometer.
Yes.
And this $200 here.
Is the fixed cost to pick us up from the hotel.
The fixed cost. So that won't change.
No.
That will remain constant. All right. So, and you mentioned a graph, but before we get to the graph, I'm thinking that we need some points. And I like tables. Tables make everything so clear, and you can pick up information, definitely.
And I agree with you. And there's something peculiar on this table.
Yes.
You're picking up that even though I'm traveling 0 kilometers,
yes.
I'm still paying something to the taxi driver.
Yes, so that would be this $200 here.
Yes.
Okay, and if I travel 1 kilometer, if we travel 1 kilometer together, and notice that $15 is added onto that $200.
Yes. And an additional $15 for one more kilometer.
For one more kilometer. So each extra kilometer we go, based on the values that we're seeing in our table, we're noticing that that $15 keeps adding on to the cost per kilometer. So in this situation, I'm thinking we multiply 15 by whatever kilometer we would have traveled. So for example, we traveled 6 kilometers. So in order to know how much to pay the taxi driver.
Yes, and that would be 6 times multiplied by 15, which would give us 90.
Yes.
Plus 200 would have been 290.
All right, so now that, and notice over in the far column there, we have some pairs of coordinates.
Yes, those ordered pairs would be what we would need to plot on our graph.
And then we'll be able to see the information on the graph.
Exactly.
Let's see what the graph looks like using some of the points on from our ordered pairs. Okay, so this point here would represent?
That would be the fixed cost.
The starting point?
The starting, yes.
Right, so at this point we notice?
He'll charge us that $200 even when we are even though we haven't moved off from the hotel as yet.
Right. And so as we go along the journey, we notice that the cost is?
Increasing.
Increasing.
And
good.
We'll speak more about that later in terms of the amount by which it is increasing.
Okay. So basically we were looking at a linear equation in everyday life. And there are so many activities that we carry out in everyday life that requires us to use linear equation without us even knowing that we're using linear equations. Sometimes we're in math class and we're wondering, why are we learning this? And you go out and use the skills and the knowledge that you have gained.
We use it every day.
And we don't even realize
yes,
it.
That is in fact true. So we'll explore a few more everyday scenarios where we'll be using linear equations.
All right, let's look at one here. Making predictions. So a situation like, schools always having bake sales to raise funds to do some activities. So sometimes we need to know how much. So for example, the Key Club going to do a bake sale, they need to know how much money they would make. So they want to make some predictions to get the amount of money that they would need for the project.
In terms of the profit, good.
Profit, yes.
So in this scenario, we're having a bake sale, as Nikisha said. We spent an initial $200, and then we are earning $150 per month from the sale of the items that we're baking.
So we can set up a linear equation to make prediction to represent this scenario here. And in the end, we could graph it.
Yes, we
could. Look at another situation.
And that would be the equation that represents this scenario.
Yes. So what about rates? Sometimes we have to make decisions based on the rates. For example, we may be offered 2 different job pay scale.
Yes, and this is important.
Yes,
because we have to be able to know how to decide on which job would be best for us in terms of the compensation.
Yes. So we'd have to see. So here we have, we're being offered $450 per week, and another company offering $10 per hour, and both of them are asking you to work for $40 for 40 hours per week. Which one would be offering the better rate of pay? Right, so we could set up a linear equation as well. This would require about 2.
Yes.
So that we can compare and contrast to make our decision.
Definitely.
Okay. So remember, linear equations every day. So what we've been talking about linear equations. What are linear equations?
Linear equations are equations of the first order.
What do you mean by first order?
Basically, that means that when we talk about order in math, we normally talk about the powers or the index.
Okay.
Yes. So when we're talking about the first order, it means that we're talking about a power or index of 1.
All right.
So these equations will have a power or index of 1.
So the terms in the equation would have power or index of 1. And these equations are defined for lines, as the name suggests, linear, in the coordinate system. And these are some examples. So we have y equal 2x plus 1, 5x equals 6 plus 3y.
And y divided by 2 is equal to 3 minus x.
And we notice that as it says, they are all of the first order. None of the terms are raised to any power greater than 1.
Yes.
And I also notice that they look slightly different. Each of them is represented in a different way.
Yes, I'm seeing some with the, especially when it comes on to the coefficient of the y term, because that's going to be important.
Yes.
The first one has a coefficient of 1.
The y term, yes.
Yes. The second equation has a coefficient of 3.
The y term, yes.
And the y term for the coefficient has a coefficient of 1/2.
1/2. Good.
Yes.
So we notice that the linear equations comes in different forms.
Yes.
Right? So we're going to be focusing on one form. But even though we might be given in one form, we can change it.
We can change it to our next.
To another form.
Some of the things that we would have learned in algebra.
All right. And we'll be looking at some of those. And one of the specific form we're going to be focusing on today is the slope-intercept form.
That is correct.
Now, this should look familiar for this linear equations to you guys in looking at slope-intercept form. The slope-intercept form is y equal mx plus b, where m is the slope or gradient or the rate of change.
And b is the y-intercept. Yes, that definitely looks familiar.
Right, and notice when we talk about y-intercept, we're talking about the point on the y-axis that the graph cuts it or intersects with the y-axis. And it's a specific point that would be our y-intercept. Tell me more about the b.
The b, that would be the gradient. I know.
No, the b, the constant.
On the b?
Yes.
We already spoke about that. That's the y-intercept, right?
Right. So that means what?
So at that point in time, it's the point at which it's a fixed point.
So no
on
change.
the graph. Yes.
All right.
So that would be similar to the fixed cost that we spoke about
Similar
earlier.
to the $200 cost that the
Yes.
taxi man would charge us, whether or not we move
Yes.
or how far we go. So let us look at an example and see if we can pick out the slope and the y-intercept.
And the M is also important to Nikisha, because we already spoke about a situation similar to that.
Yes.
In terms of the rate of change.
Right. Which was the
rate at which
$15.
it was increasing.
The $15.
So that would have been our gradient.
Yes. So
So
in this equation, y equal 2x plus 1. Can you identify the slope or the rate of change?
I am saying the slope or rate of change would be 2 in this situation.
And what would be your y-intercept?
And the y-intercept would be 1.
Correct. That would mean the graph would cut the y-axis at 1. So that would be your y-intercept, b equal 1. So basically, in some, let's look at the different parts. We were just looking at that. So this is what it would look like on a graph. For example, in this case, our gradient or rate of change in this case is 2/3.
2 is...
3 halves.
3 halves,
3
yes.
halves. And notice that we have this right triangle formed here, Tyrone.
Oh, that looks like what we would normally do when we are finding the gradient
Yes.
on the graph paper.
Yes. So the 3 would represent...
The 3 would represent the vertical movement,
Yes. And the 2...
or some people call that the rise.
The rise, yes.
And then the 2 would be the horizontal movement, which would be the run.
The run. All right, good. So let's continue. All right, it's lunchtime and we're having patty and orange juice today.
Wow.
It's been a while. We've been in quarantine for so long. We haven't been to school. And it's so good to be back to buy patty and orange juice. So tasty.
And I love patty, especially the tasty patty.
Really?
Yes.
Well, it don't matter whichever one to me. I just eat any patty as long as... So anyway, you notice how the price was so expensive?
Yes, this is not the price I normally pay for patty.
Yeah, patty and juice is like, said, everything just skyrocket. Look at what, so you got 2 patties and 1 box of orange juice for $540.
And you paid for 1 patty and a box orange juice for $320.
Yes, it's so expensive these days. But I don't even know, you see, because I was so hungry, I didn't even check to see how much each of the item costs. I just give the lady my money.
Anything them want, charge me, they just hungry, as you said.
Yes, but now that I'm thinking about it and looking at what I have left, we need to figure out how much this costs so we know how much to budget for tomorrow.
But I think between the both of us, we can figure that out.
Yes. Based on what we have been doing before, you think we could set up some equation to sort this out?
Yes, this looks like some equations.
Yes. All right. So, first of all, let us establish some points, some things here. So we're going to let X be the cost of 1 patty.
Okay, sounds good. And Y be the cost of 1 box of orange juice.
Okay. Now, with that said, let us see what the equation would look like for 2 patties and an orange juice. And that would be equal to $540, and that would be your purchase.
That is what I bought, two patties and a box of orange juice.
So that's 2x plus y
and I paid
equal
$540.
for $540.
And you bought 1 patty and a box of orange juice, and you paid $230.
So that's x plus y equal 320.
And we're emphasizing that X and Y in this situation has to do with the cost of each.
Cost of each item.
Yes. So 1 patty cost X is represented by X, and 1 box of orange juice, the cost of it is represented by Y.
Awesome. Okay, so let's see notice the two equations. First, we had 2x plus y equal 540. Now I'm seeing y equal 540 minus subtract 2x. What happened here?
Remember we were talking earlier about the slope-intercept format?
Yes. Oh,
and
yes.
we wanted y equal to something?
Yes.
So we are re-expressing in this situation using what we would have learned in algebra class, specifically transposition.
Ah, yes, transposing. So what operations did we do to get this 2x from the left side over to the right side?
I'm thinking because it is a plus 2x,
yes,
I would need to take 2x from both sides.
And that would
so
give
subtraction
all
would
right.
be the operation.
Okay. And here we add x plus y. This is my purchase equal 320. It's not in the slope-intercept form, y equal mx plus b.
Yes.
So I would therefore need to do transposition.
Transposing again.
Okay.
So we can subtract x from both sides.
Yes.
And it now becomes y equal 320 minus x.
Good. So now we have these two equations to work with. Both of them saying y equal to terms. All right, so looking at this, can this tell me the cost for each item, seeing that I have two unknowns here?
That's not normally how we normally solve equations. We usually only have one unknown.
Yes. So how can we sort this out?
Let me think about it a little bit. Oh, yes. Remember in math class when we were doing algebra again, we discussed simultaneous equations.
Oh, yes.
When we had two unknowns for two equations.
Oh, yes, right. So we have two unknown simultaneous equations. Yes, that would be quite useful for us now to find out the cost for each item. All right. So what's the first thing we want to do to solve here? I'm thinking a table would be useful so that we could maybe generate some values.
Okay, and as we had discussed in terms of simultaneous equation, we know that there are different ways we can actually solve simultaneous equations.
Yes.
So we have...
Oh yeah, I remember the elimination method.
Yes, the substitution method.
Yes, and as we're going to be, and the matrix method.
Yes, and we are going to be looking at the graphical method today.
Oh, okay.
And I personally love graphs, so
yes.
I'm so excited.
All right, but don't get too excited, Taron. Just let's get back to this and take it one step at a time. So now we are looking for some y values because we want to plot our graph. So x values, we have 0. When x is 0, we notice that if we substitute 0 in the equation, y equal 540, subtract 2x, it would mean 540 minus 2 times 0, which would be 540.
I'm realizing that you're substituting that 0 into the equation.
Wherever x is.
Where x is to do the solution.
Yes. And so we'd have 540 for our y value there.
But that makes sense. But we are just playing around at this point, because we're not sure what the cost of the patty and the box of juice is.
No.
So we are just finding some possible costs. And we are looking at the case when the cost of one patty is 0.
Yes.
Although we know it wasn't 0.
No.
But if it was 0,
that means we would pay the 540 just for the orange juice.
That means you paid 540 just for the orange juice.
And we know they're not giving out no free patty here. So say for example, if say for instance the patty cost $100, it would mean that substituting that 100 for x in 540 subtract 2x, it would be 540 subtract 200 because 2 times 100.
And therefore, a box of orange juice would cost $340.
If it were being sold for a patty for $100.
Yes.
All right. What if it were sold for $200?
That would be 540 minus 2 times 200.
Good.
Or 540 minus 400, and that would be $140 for one box of orange juice.
Okay. All right, so this is your purchase. Let us see what it would look like for my equation, my purchasing situation, where I bought one
patty
And
and
one
one box of orange juice.
Yes. Using the same values that you used, notice the difference in the cost. So when your patty was for zero, you didn't pay. Your orange juice cost for 540, but mine is 320.
That looks a little bit weird.
Well, remember you bought 2 patties, I only bought
Oh,
one.
yes.
And so when it is the cost for the patty is $100, supposing it is $100, and we substitute that value for X in the equation, we notice that the orange juice, after subtracting 100 from 320,
Costs $220.
would be 220. And if we substitute 200 for X in the equation, subtracting that from 300, it would be 120.
But wait, Nikisha, didn't we buy the patty and the orange juice from the same place?
Yes.
So shouldn't we be paying the same amount of money for the orange juice and the patty?
Definitely. Most definitely.
But I'm not seeing where any of these values found for the orange juice match the values that you could possibly have paid for your orange juice.
I understand. But remember, we're not yet finished with this. Let's take the experiment a little further.
Okay.
Remember, you said you like graphs?
Oh, yes.
So let's get into that
definitely.
exciting part. So, looking at these 2 equations graphically, this first one represents your purchase.
Yes.
And this other graph represents my purchase.
Okay, so I am seeing the 2 graphs. The first being a representation of what I purchased,
Which is a line y equal 540 minus 2x.
And the second would be the line representing your purchase,
Yes.
which would be y equal 320 minus x.
And it's very important to label our lines as we're working so that we can keep track of what we're doing.
But Nikisha,
Yes.
as we were discussing before,
Yes.
if we both purchased it from the same place, we would have needed to pay the same amount for 1 box of orange juice and 1 patty.
Yes, it would mean that.
So there must be at some point in time, based on our analysis, that
Yes.
these 2 figures are going to be the same.
Most definitely. And I'm thinking that if at that point both of them should be the same, it would mean that there'd be some intersecting taking place.
Yes.
Think about sets. Remember, they share the things in common.
Okay.
So when I look at the 2 graphs here, I see that the 2 graphs intersect.
At this point.
Ah. So that point would be the cost of the 1 patty and 1
Yes.
orange juice.
So right here is a point of intersection marked in the red.
So I'm
Good.
seeing 220 for the X value, which was the cost of the patty, 1 patty, and 100 for the Y value, the cost of an orange juice.
Yes.
And you know what else I'm picking up from the graph? I'm picking up the Y-intercepts.
Oh, yes. I didn't even realize that they were there.
Yes, the
Yes.
Y-intercepts are here, and these are the constants.
Those were the constants.
Yes, so notice here on my graph, 320 was my constant, my Y-intercept. And here on your graph, 540 was your Y-intercept.
Yes, you are indeed correct.
Yes. So this intersection here of these 2 graphs would provide a solution.
Let's do a quick check. You bought 1 patty and a
Yes.
box of orange juice.
Yes.
So 220.
Right, so if we were to substitute those values
Values.
in my equation,
You would get back the 320 for
I
your
should
purchase.
Yes, I should.
And I bought 2 patties and a box of orange juice.
So
that
if you
would be-
substitute those values in your equation, you should get 540.
Oh, okay.
All right. So we have been talking about simultaneous equations, and you notice, Tyrone, that these are what? 2 or more?
There are two or more linear equations with at least 2 unknown variables.
Yeah, that could be solved at the same time.
And they can be solved at the same time.
Right, because
Yes.
good. And what else we know about simultaneous equations?
And we had mentioned this before. We could solve it using the graphical method,
Yes.
as we would have just looked at a while ago.
Uh-huh.
We could use elimination, substitution, or even matrices.
Awesome. So simultaneous, solving of simultaneous is very versatile. We have a lot of variety to choose from, however way we want to solve them.
Yes.
All right, so that's the focus of our lesson today, solving simultaneous equations graphically. So let's get into that. Now, with simultaneous equations, there are different types of solutions. We have unique solutions.
There are infinitely many solutions.
Or no solution.
Wow.
No, what we mean by unique solution and infinitely many solution or no solution?
So in this graph, we have a unique solution because it has only one point of intersection.
Just like the graph that we just did with the
Yes.
patty and the orange juice.
Yes, so that situation has one unique solution.
Okay, so just 1 point. All right, so we talk about the unique solution. Let's look at infinitely many solution. Infinitely mean what, Tyrone?
Many, multiple, a lot.
That going in. Ooh, this one looks different. I just see it's two equations, right? Remember?
It's two equations.
Yes, two lines.
But they seem to be overlapping.
Right, they're overlapping on each other.
Yes. So the graph seems to be coincidental, right?
Yes. So they're lining up. All the points are collinear. They're lining up all the points along each of these graphs. So it's just thinking of two lines coming together and lying on top of each other.
But Nikisha, if the two lines, all the points on the two lines are the same,
Yes.
aren't they basically the same line?
Exactly. Exactly.
Okay, so these two equations actually are different ways of expressing the same equation.
Yes. So it therefore means that, as we said, infinitely many solutions. And the third one we mentioned was inconsistent equation, where there is what?
There is no point of intersection.
No point of intersection.
And
Two lines come to mind where they never intersect, they never meet.
parallel lines.
Parallel lines.
Yes,
So
I
once
agree.
they get in parallel lines, it means there is no solution. Okay, so this is what you were just saying. Exactly one solution.
The two lines have one point of intersection.
Infinitely many solutions.
The lines are completely identical.
Yes. And no solution.
They are parallel and have no point of intersection.
Great. All right. So let's look at an example. So we can write equations of the line. So say if we have this equation of a line 2x plus 3y equals 7 in the format y equal mx plus c or b, which is
the slope-intercept format we spoke about earlier. And that has some merit because it's easier for us to pick up certain key things from the slope-intercept format.
Right.
The gradient and the y-intercept and all of these things that makes it easy for us to sketch our graphs.
To sketch our graphs. Very good. So basically we need about 3 points to sketch our graph, a line graph. Yeah, good. So by transposing for y, and we did some of that. So looking at 2x plus 3y equals 7, doing some inverse operations on both sides, trying to isolate y.
Yes, if I am trying to transpose 4y, it means that I'm going to have to find out a way to get the 2x on the other side of the equation.
Okay.
So I could do that by subtracting 2x from both sides, as done in this situation.
And when we do that, it follows that we would have 3y is equal to 7 subtract 2x. But is y yet by itself?
No.
And furthermore, I noticed that you have changed around the order of the terms.
And that's perfectly okay because they are basically representing the same thing as we did before. The 7 is still positive and the 2x is still negative.
We just do that so it looks like it's in the y-intercept, the slope-intercept form.
Yes.
Okay, awesome. So we have 3y. So we have not yet isolated y. So what's the next step?
I'm thinking 3y is 3 multiplied by y.
Yes.
So we would have to do the inverse operation, which would be division.
So we would therefore divide both sides of the equation by 3, and that would then isolate y. So we'd have y equal negative 2x
plus 7 all divided by 3.
All right, so we have transposed this linear equation to the slope-intercept form. So using that equation, again, we can find values and plot graphs. So substituting for x, -3 in the equation, we see that would be -2 multiplied by -3 plus 7 all divided by 3.
And that would give us 6 plus 7 all divided by 3. And that would be 13 thirds.
13 thirds for y. So if I substitute 0 for x in the equation, that would be -2 multiplied by 0 plus 7 all divided by 3.
And that would be just 0 plus 7 divided by 3, or 7 thirds.
For y. So if I substitute +3 in the equation, that would be -2 multiplied by 3 plus 7 all divided by 3.
That would be -7 plus
-6.
-6 plus 7 all divided by 3.
Yes.
And that would be 1/3.
1/3. Now, and notice, does it matter which values we use for x? How we decide, what do I use to decide which numbers to use for x values to substitute? Does it matter?
Most times it really doesn't matter, because what we are trying to do is just to get a line.
Yes.
And we just need the ordered pair for x and y.
Yes.
And once we have a number of them, we have enough points to sketch our line.
Okay.
To plot our line.
Okay. So let's see. So now we have x and y values. So we can look at the graph of that equation.
Whoa.
So we're just using 3 points.
Yes. So we used when x is -3, we use when x is 0.
Yes.
And when x is
So +3.
+3.
Yes. Okay. So that's not hard. So, and remember to label our lines. Label your graph with the equations. Okay, so now we have a pair of simultaneous equations, and we're going to solve this graphically. So we have 3x minus 2y equal 12.
But Nikisha, this almost looks like a CSEC question I did when I was practicing math the other day for the exam.
It does?
Yes, it
Well,
does.
it's not strange because you know CSEC. So let us see if what you did.
Let's see if we can solve this question using the graphical method that we would have learned today.
And see how it works out, what it looks like.
And see how it works out. Okay. So, firstly, we're going to start off by making y the subject of the equation.
Because it wasn't, right? We're going to make y the subject of these two equations. So focusing on equation 1.
Okay. So that is what we have for equation 1. 3x minus 2y is equal to 12.
And remember, we want to isolate y, so we're going to do the inverse operation for 3x, and we're going to subtract 3x from both sides of the equation, leaving -2y equal 12, subtract 3x.
And then, because, as Nikisha said, we're trying to get y isolated, we would divide both sides by negative.
But before we do that, we just want to fix it up so it look in the slope-intercept form.
Yes, we can do that as well.
Move around the terms.
And then we can divide by -2.
Both sides of the equation. So it therefore means y would be equal to -3x plus 12.
all divided by -2.
And we can tidy this some more.
Yes. And we would do that by multiplying the numerator and denominator by -1.
-1, yes. And therefore, we now have a final equation, y equal 3x minus, subtract 12, all divided by 2. Let us turn to equation 2.
This one looks a little bit easier.
Yes.
So we have, starting off, 2x plus y equal 1. We can transpose by subtracting 2x from both sides.
Okay.
And we are left with y is equal to 1 minus 2x.
1 subtract 2x, okay. So I noticed that my c, so we can therefore tidy this up a little bit better, moving around the terms. So we would have, okay, all right, we didn't need to move that. So let's find some values for y, starting with the first equation that we got. Substituting negative 5 for x in the equation 3x, subtract 12 all divided by 2 would be 3 multiplied by negative 5, subtract 12 all divided by 2.
And that would be negative 27 divided by 2, which is negative 13.5.
For a y value.
For our y value.
And for our x value, substituting 0 in the same equation, we would have negative 3 multiplied by 0 for x, subtract 12 all divided by 2.
And that would be 0 subtract 12 all divided by 2.
Right.
Which is the same as negative 12 divided by 2, or just negative 6.
And if we were to substitute positive 5 for x in the equation, it would be 3 multiplied by 5, subtract 12 all divided by 2.
And that would be 15 subtract 12 all divided by 2.
Okay. And that would give us
3 halves.
3 halves.
Or 1.5.
All right, so now we have some x values and some y values. So we can plot a graph for this one. But before we do so, let's check out the other equation. All right, so if we have x values negative 5, substituting in this equation y equal 1 subtract 2x, it would be 1 subtract 2 times negative 5. Go ahead.
And that would be 1 plus 10, which is just 11.
And if we should substitute 0 for x in the equation, it would be 1 subtract 2 times 0.
And that would be 1 subtract 0, which is just 1.
All right, and if we were to substitute 5 in the equation, it would be 1 subtract 2 times 5.
That would be 1 subtract 10, which is negative 9.
Awesome. So now we have points for our two equations.
Yes, we have the x values and the y values for both equations.
For both equations. So let's graph them and see if they intersect.
Oh,
and
we
where.
hope it does.
Yes. All right. And they do intersect. At this point.
At this point, let's see if the students at home can pick up what the value of this point is.
Maybe, I'm not sure if they're able to see it. All right. So based on our reading of x values first and our y value following, we would get?
The x value to be 2. And the y value to be negative 3.
Awesome. So we have a point of intersection, and this is called, it's one intersection, 1 point.
It's our unique solution.
Unique solution. Awesome, awesome. Let's look at another example. And this time, a CSEC question. Well, you said that one was CSEC too.
Yes.
All right, this is from May 2015. Oh, some lovely mangoes and pears.
Whoa.
Wow.
I love those. Well, I like the mangoes more than the pears.
I like both of them. I just love fruits. They're just so juicy and delicious. All right, so let's hear the situation that was presented about mangoes and pears.
4 mangoes and 2 pears cost $24, while 2 mangoes and 3 pears cost $16.
Okay, price not bad. So we can, it therefore means that we can set up simultaneous equations because we have two situations here.
We have 2 situations.
So we need 2 equations. So let's assign some, the other instructions.
They're asking us to write a pair of simultaneous equations in x and y to represent the information. And we're supposed to state clearly what x and y would represent in the situation.
Awesome.
Finally, we're going to be graphing them.
Okay. All right, so first of all, let x be the cost of 1 mango and y be the cost of 1 pear.
Okay.
All right. So looking at the equation, so it's 4 mangoes and 2 pears for $24. So 4x plus 2y.
Okay.
Equal
the x being the cost of 1 mango. So that 24 is the total cost for the 4 mangoes and the 2 pears.
Good,
Okay.
good.
And for the next one, it would be 2x plus 3y is equal to 16.
To $16. So right. So now we have 2 linear equations. So first thing, we want to make y the subject. So let's isolate y by using inverse operations.
Okay, we can go ahead and we can subtract 4x from both sides, and that will result in 2y is equal to 24 minus 4x.
So 24 subtract 4x.
And we can go ahead to divide both sides by 2.
Awesome. And that would have y equal
12 subtract 2x.
Okay. Let's look at the second equation. So 2x plus 3y equals 16. Let's isolate y.
And again, we would need to find a way to get rid of the 2x. So we subtract 2x from both sides.
Inverse of adding, yes.
Inverse of the addition.
And that would leave
3x is equal to...
3y.
3y is equal to 16 subtract 2x.
Good.
And we just move them around just so that we have them in a good format.
Yes.
The slope-intercept format. And then we would still need to do something because we have a 3 for the coefficient
Of y.
of y.
And we want that to be 1, so it therefore means that we would just divide both
by
sides
3.
by 3, as we're multiplying y by 3. And that would equal to?
Y is equal to negative 2x plus 16, all divided by 3.
Awesome. So now we have our two equations where y is a subject. So let's create some tables of values for both of them. So in this table, substituting these values for x, when x is 0, we note that y is 12. When x is 2, y is 8. When x is 4, y is also 4. And when x is 6, we find that y was 0. So these are the points that were generated for this equation.
For the first equation.
For the other equation,
we're doing the similar
substitution. Yes.
And we substitute 0 into the equation, and we get
5 and 1/3. And then when we use 2 for x.
But Nikisha, quickly, how did they get the 5 and 1/3?
All right. So substituting 0, so 0, negative 2 times 0 is 0.
0.
Plus 16. So it will be 16 divided by...
So it would be 16 thirds, and when you simplify that, it would be
5 and 1.
3 into that goes 5 wholes and 1 remainder. So
awesome.
It's 5 and 1/3.
So we have a mixed number there.
Yes.
So when x is 2, y is 4. And when x is 4, y is 2
and 2/3.
And following down in the same order. Okay, so now that we have our points, let's see what our graph looks like. So note this is the first equation. And we are labeling them. And then notice the point of intersection.
Yes. So you can see here that the point of intersection is 5, 2. 5 being the value for the x.
Which was the mango.
Which was the cost of one mango. And y being the cost of...
The 2 being the value of the y, which was the cost of the pear.
One pear.
One
yes.
pear. Yes. So here we have a unique solution. So we have solved that pair of simultaneous equation graphically.
Yes,
Ta-da.
yes we did.
Awesome. All right, so now that we have acquired that skill, let's see if we can do one last one.
Definitely.
So now we have these two, and the first step, remember, is to make y the
subject.
Make y the subject.
Let's see if they...
So let's do that quickly.
Let's do that quickly. So basically, what we want to do is to subtract 2x from both sides.
So subtracting 2x from both sides, we're left with...
we get
y
is equal
3.
to 3 minus 2x.
All right.
Awesome.
So let's look at this.
And we just switch that around to put it in the slope-intercept form.
And the second equation, subtracting 5x from both sides of the equation, we're left with negative 2y equal 12 subtract 5x.
And we switch the
terms around
to get that in a better format. And then we're going to be dividing both sides
by...
We're going to be dividing both sides by negative 2.
Awesome.
To get the value of
y.
Y to be isolated.
So now we have generated the two equations in the format y
And then,
equal mx plus b.
but just as before, you realize that we had a negative number on
Oh,
the
yes.
denominator.
Negative number in the denominator.
And we as mathematicians, we don't like to have negative numbers
No.
on our denominator.
So to fix that,
So to fix that, we'll multiply both numerator and denominator by -1.
and that will give us positive values in our denominator. Awesome. All right, so let's use the tables to generate values for some points so we can plot. So for the first equation, when we use -5 as our x value, we get -2 multiplied by -5 plus 3.
That's 10 plus 3, and that would be 13.
When we use 0 for our x value in our equation, we get -2 multiplied by 0 plus 3.
And that would be 0 plus 3, which would be 3.
And when we substitute +5, it would be -2 multiplied by 5 plus 3, and that would give us?
-10 plus 3, and that would be -7.
All right, so that's the first equation. Let's look at the second one. Now, if I were to use 4x,
we're using the same values, so -5. So it would be 5 times -5 minus 12 all divided by 2.
We give a y value of -37 divided by 2, which is the same as -18.5.
Using 0 substituted into the equation gives us 5 times 0 minus 12 all divided by 2.
And that would be 0 subtract 12 all divided by 2, which would give us -6. When we use +5 for x value,
that would be 5 multiplied by 5 minus 12 all divided by 3. That would be 13,
yes, 13 divided by 2.
2.
6.5. So now we have our two values set of points so that we can use to plot our graph. And
when we plot our points, we are getting one unique solution again.
One unique solution. Awesome.
And let's see what the values of that would be. So for the
point of intersection.
For the point of intersection, we're getting x to have a value of 2 and y having a value of -1.
-1. So basically, we can say the solution is for simultaneous equation graphically is where the graph intersect each other. The point where the graph intersect each other. All right. So let us summarize what we have looked at today. Sorry about that.
So basically, we started off by making y the subject. Then we substitute key values of x into the equations to get our points that we're going to plot on the graph.
Yes.
Then that would give us for the first line. And we would need to repeat those steps to get the graph of the second line. And then we identify the point of intersection if there is a point of intersection.
All right. So also, we notice that the graph of every linear equation in two variables is a straight line. Additionally, y is equal to mx plus b. Y equal mx plus b is a slope-intercept form,
yes,
where m is the slope of the line and b is the y-intercept. That's where the y-axis is crossed by the graph. And we know that there were 3 different types of solutions that could be arrived at using solving simultaneous graphically.
We can have one unique solution when it intersects at one point. We can have no solution when the lines are parallel. And we can have infinitely many solutions when the lines overlap